So motion in one direction. What we're talking about here is that if we have simple motion, so we're going from point A to point B, either purely horizontally or point A to point B purely vertically. We're not talking about things that travel through the air in both dimensions yet. Okay, we're just talking about horizontal motion or vertical motion, not a combination of the two yet. Okay, so when I talk about motion in one direction, it doesn't mean like just walking east or just walking west. It just means we're moving purely horizontally or purely vertically. Okay? All right, so chapter 2. There's two main sections in physics, broken up into mechanics and dynamics. Mechanics is the study of motion, okay? And it's related to the force and the energy that goes into it. Okay, so the mechanics of something, we've heard that word before? Mm-hmm. Mechanics, right? How it moves, how it works. That's what we're looking at, the motion of the object. Dynamics, on the other hand, dives a little bit more into specifically the forces behind it. Okay, what's causing it to move in that direction. We are right now only really focused on, okay, yes, it's moving. How fast is it moving? Where's it moving to? Where's it going to end up? Things like that. Okay. So mechanics itself is split up into two parts. The mechanics talks about motion and force. I think I said this wrong, actually. I'm sorry. Mechanics is split up into two parts. Kinematics was focused on the motion, and here's where dynamics comes in, which talks about the forces. So I'm sorry, I misspoke the first time. Mechanics is broken up into kinematics, which is a description of motion, and dynamics is the forces behind it. So I misspoke the first time I said that. Okay. So this, essentially, this mechanics section is going to be like the whole year's worth of materials, right? We're going to focus on the motion of objects and the forces behind them pretty much for the whole year, right? We don't deal a whole lot in this class with electricity and light and things like that. So we are talking specifically right now about translational motion. So like in geometry, what happens when you translate something?
Just move it.
You just like move it, right? You just slide it. So that's what we're talking about. Translational motion is motion without rotation. Okay, so it's not necessarily just something that's sliding. It's something that's moving very simply from point A to point B without any rotation. Okay, we'll get into things that spin much later in the year. Okay, and to go with translational motion, we're looking right now at things that move along a straight line path. So we don't have any arcs, nothing else crazy going on just yet. Okay, things that move very simply from point A to point B. Whenever we look at a representation or a measurement of motion, it has to be made with what we would call a frame of reference. So most of the time, like the earth is our frame of reference, right? We're standing on the earth watching something happen. Okay? Or we're standing at a specific location watching something happen. And that's most of the time our frame of reference. And most of the time it's something we don't even think about. Okay, but I'm going to talk about a few situations in which you have a change in your frame of reference that would affect how you view motion. Okay, so with respect to the earth is going to be our normal frame of reference. That's not a key phrase that you need to know, okay, but I'm just kind of talking you through what we're looking at here. Okay, with respect to the earth. If you're no longer standing on the earth, that becomes your new frame of reference. So if you're riding in a car, or if you're riding on a train, or if you're in a roller coaster, that's your new frame of reference, right? I'm going to show you an example here pretty soon, but let's say you're driving in a car and you meet a car that's going the same speed as you. Does it look like they're going 60 miles per hour? Not really, right? It looks like they're going pretty slow because you feel like you're going kind of slow, right? Does that make sense? Have you ever experienced that before? And let's say you meet, or someone passes you going a lot faster than you. Does it look like they're going 85 miles an hour, or does it look like they're going 15? Because that's how much faster they are than you. Right? Do you know what I'm talking about? Okay, if you stood on the road and watched somebody go 85 miles an hour, it would look a lot faster than when you're in a car and somebody passes you going 85 miles per hour. Because your frame of reference is different. Okay? Okay. we're going to look at an example here pretty soon, but I want to make sure you understand that every measurement we give in terms of motion, so how fast something is going, where it's ending up, things like that, they have to be given with a direction along with its speed. Okay, so luckily with physics, more often than not, our like sign is used as direction. So negative would mean it's moving south or downward or west, and a positive direction would be moving east, north, or up, right? So we can usually use our positive and negative sign to help us indicate direction. Sometimes you'll use the cardinal directions, and sometimes you'll just use the sign. Okay, but it is important that in all these measurements we include direction. Okay, so let's look at this truck example. So here you are with your little baseball glove. This truck is at rest and they throw the ball at you 10 miles an hour. Okay, so it appears to you to be traveling how fast? If you could calculate that in your brain, how fast would it be going? 10 miles per hour, right? You're standing still, nothing's changed in terms of your frame of reference. Now let's say the truck is moving toward you at 10 miles per hour and they throw the ball at 10 miles per hour. How fast does it seem like that ball's coming? 20, right? Twice as fast because the truck is moving toward you and the ball is moving toward you. Okay, does that make sense? So it changes our frame of reference when something is in motion. And if the truck moves away from us at 10 and the ball's coming at us at 10, it looks like the ball's taking a long time to get there, right? It looks like it's moving a lot slower. Okay, so that's what we're talking about, frame of reference is changing. Okay, does that kind of make sense? Have you experienced that before? Okay, I'll give a few more examples here pretty soon. Okay, in physics we use a set of coordinate axes to represent our motion models. So I'm going to pull up a graph here pretty soon, but we want to place our origin always at 0, and we're going to use cardinal directions to label. So I'm going to just pull up the picture here. You don't need to write down all those bullets. Okay, in physics we're going to draw very simple motion diagrams a lot, and you don't have to draw a full here coordinate system, but we're always going to choose the start of our motion to be the origin. Right, wherever the motion is starting from. Let's say I'm standing on top of a cliff, right? So here I am up on a cliff, okay? So where I'm starting, that's going to be the start of my motion. And if I jump off the cliff and I go here, right, that's what I'm looking at. I'm going to place the origin where my motion started. Okay, does that make sense? Okay. So usually we're going to get to pick where our motion starts from in terms of where we place it on our coordinate graph. But using a coordinate system like this is important to us. So let's help me label the cardinal directions. Here is north, east, south, and west. Okay, how many of you know your cardinal directions? Yeah, north is going to be a positive direction. What if we're moving horizontally? What's going to be the positive direction? East. Good. And so then if something's moving west, we're going to consider it negative, and south, we're going to consider it negative. Okay, so those are things that we need to remember in terms of, we won't always have to use cardinal directions. We can use signs to help us indicate a positive or a negative direction, positive or negative motion. Okay, so we need to remember north is positive, east is positive, south and west are our negative directions. Okay, we're looking today at motion in one direction along the x-axis. Okay, so we're going to look at any position along the time. Let's say we've got a little person here. Here's our x-axis. Here's 0. Right, here's my x-axis. So that means that any point along this guy's path, he's going to be on the x-axis. So we would be able to tell where he is at any point because he's going to stay on the x-axis. Okay, because he's moving purely horizontally. Does that kind of make sense? Okay, I know that verbiage is not perfect, but as long as we're looking at motion in one direction, we can assume anywhere they are is going to be along the x-axis or along the y-axis. Okay, so when we're talking about how far they've traveled, we have two different terms that we can use to help describe to us how far they have traveled. Okay, and displacement is the first. Displacement is called the change in position of the object. And what I want to tell you about this definition even further is that essentially the better definition for this is how far you end up from where you started. Okay, because there's a big difference in the definition between distance and displacement. Distance and displacement mean two different things. Displacement is specifically how far you ended up from where you started. Okay, so if I run one lap around the track, what's my displacement? 0, right? I'm ending up in the same place that I started. So I achieved nothing, right? My displacement would be 0. So that's a little tricky. I think it's kind of tough for us to wrap our brains around, but displacement is specifically how far you ended up from where you started.
So if you only went like halfway around?
Yeah, you would still have a displacement of 200 meters, right? Because you're ending up at somewhere different from where you started. Okay?
This isn't going to go well.
Okay, so we'll just think about that. So but if I asked you for my distance, if I ran one lap around the track, you'd tell me 400 meters, right? So I traveled a distance, but my displacement is 0. That's tricky. Okay?
Okay, but I have another question.
Yeah.
After that. So say you're on a track and it's like curved, the distance would be 200 meters because that's how far you're going, but would the displacement be more since it's like
Yeah, it could be the hypotenuse, like the straight line from that. Yeah, that's a good question. Okay, so let's look at this example. Joe walked 40 meters east and turned around to walk 50 meters west. So I'm going to draw this out here. 40 meters east, then 50 meters west. So let's say she walked 40 meters. And when we depict motion, we do it in the form of an arrow called a vector. And we'll talk about that in a little bit. But let's say she walked 40 meters. So 1, 2, 3, 4 meters, 40 meters east. From there, she turned around and walked 50 meters west. So 1, 2, 3, 4, 5. So her final displacement was what? 10 meters what?
West.
10 meters west. So 10 meters. Wow, that's hard to see. Sorry. 10 meters west. Okay, but the total distance she walked was what? 90 meters. Okay? Different. So distance equals 90 meters. Displacement equals 10 meters west. The thing about the difference between distance and displacement is displacement has no direction. So you're just talking about the total that they traveled. It has no direction. Displacement tells us exactly how far we ended up from where we started, or where we ended up from where we started. Okay, so total distance and total displacement, we talked about those. Displacement must have both magnitude, which is the size or the length or the whatever, and direction. So when we talked about total displacement being 10 meters west, this is our magnitude, and this is our direction. And this is a big one. Any measurement that has to have both magnitude and direction is what we call a vector. Okay, so vector is a measurement that must include both magnitude and direction. Okay, that's a big one. We have a lot of different types of vectors. Okay, so a vector is a type of measurement that has to include both magnitude and direction. Displacement is the first example we encounter of a vector. Okay, does that make sense? We represent vectors with an arrow. Okay, so that's why we drew our walking distances with an arrow. Okay. Oh, I just said it out loud before the thing did it. And I'm good. Just kidding. Okay, represented by arrows on diagrams. So we draw our vector. We draw our vector with an arrow, and the arrow is, I guess you know an arrow had this much about it, but this is called the tail of an arrow, and this is called the tip of an arrow. Okay, we didn't know arrows were that complex, but they are, apparently. So when we draw our arrows, we draw them in the direction of the motion. Okay, don't do anything weird. Don't draw it backwards. Draw them in the direction of the motion. So if we're walking east, and then north, and then west, and then south, and then east again, or whatever, okay, we draw them in the direction of the motion. So if we walk that whole path, we were trying to find our final displacement, Here's where we started. Here's where we ended up. Right? There's our displacement vector. Okay? We don't care about the path it took us to get there. We care about where we are from where we started. That makes sense? Okay. So vectors can be both positive and negative because they include direction. Okay? So if I tell you that she traveled negative 30 meters, where does that tell you that she traveled? You have two possibilities here. Yeah, either south or west. She ended up either south or west, 30 meters from where she started. Okay, so if you give me a negative like that, either the problem is specifically horizontal or specifically vertical, that's fine. If we need to know that they went west, you would just drop the negative. Oops. Drop the negative and you would tell me west. Okay, but not both. Okay.
So you're saying that you could do like negative 30 meters east, and that means something.
Yeah, but that's
weird.
That's icky. Yeah.
Yeah, I got it.
Yeah. Too many double. Yeah.
Yeah.
But yes, you're right.
Okay.
Okay. So either a positive or a negative, or a cardinal direction, but not both. Okay. All right. Distance is what we consider a scalar type of measurement. Okay. And a scalar measurement only includes magnitude. Okay. So it's only the number. Okay. Magnitude only. So scalars do not include direction. So distance is an example of a scalar quantity, a scalar measurement. And we deal with scalars much less often. We're going to start getting some variables here and getting some equations, but when we talk about displacement, like in the x direction, we would talk about displacement this way. This is how your book depicts displacement. The change in direction in the x direction. Right? Delta means change in. X means horizontal distance. So if I was going to try to talk about the change in a vertical distance, what do you think the variable would be? Delta y. That's right. Okay? So some physics textbooks would say delta d for displacement, right? And then you would just talk about, you would make it vertical or horizontal depending on the problem. But your book splits it up into delta x and delta y. Okay, the two physics books I have do it differently, so hopefully I won't slip up. Usually I don't, but it can happen. Okay, so when we're talking about displacement, which is the distance, right? We're going to label them with delta x and delta y. Okay, so that's change in our displacement. We're going to start with horizontal direction, and then we'll go to vertical direction later. Okay, so we'll start with delta x in our equations. Okay, moving into speed and velocity. If you want to come grab an equation sheet. Okay, so speed and velocity. Speed and velocity are two different things, believe it or not. One's a scalar, one is a vector. Okay, what are two things that vectors have to have? I'm going to ask you this question so many times you're going to say magnitude and direction. Good. Okay, I'll ask you so many times you'll get so sick of it. Speed is how far an object travels in a given time frame. Bless you. Okay, I don't really want to talk about that. Okay. So speed is how far an object travels in a given time frame. Average speed, there's not really a huge difference between speed and average speed. We don't talk about, there's something called instantaneous speed, which can get down to the derivative of time. And we don't do that, right? Those are instantaneous little specks of time, and we don't really concern ourselves with that. Okay, so speed we're looking at is essentially average speed. Okay, and what we're talking about when we say average speed is the total distance traveled divided by the total time it takes to travel. Okay, they're basically the same definition, right? How far you traveled over a certain time. Okay, that's what speed is. Okay, so if I traveled 240 miles in 4 hours, my average speed is 60 miles per hour. Does that mean that I went 60 miles per hour for every single second of that trip? Right? I never hit the brakes. I never sped back up. That's not really what that means, right? This is telling us that over that 4-hour trip, my average was 60. And that's what we're concerning ourselves with. The smaller the time frame, the more precise your speed's going to be. But if we're looking for average speed, that means we're talking about the total distance divided by the total time. Okay, that even includes like if you stopped. Maybe you stopped for 5 minutes in there, right? But we don't know that. That's total time. Okay, so that includes, you know, stops or whatever you had to do along the way. Okay. Velocity, however, is the vector quantity of speed. Okay, so speed is a scalar. Velocity is a vector. Convenient. V, V, S, S. Okay, so you can remember which one is which. Speed is scalar, velocity is vector. Has to have what?
Direction.
Direction. Good. It has to have direction. So we use displacement instead of distance. Okay, we already answered that. Good. Here's our equation. Oh, your first physics equation. Oh.
Madness.
Oh. Good. Meters, right? Displacement is measured in meters. Time is measured in seconds. So our velocity unit is meters per second.
Like north, south, east, west, please.
You will have that, but that's not part of the unit itself. That just gets tacked onto the end. Mm-hmm. Amanda asked a good question. The north, east, south, west isn't part of the unit. It's just the direction that gets tacked on at the end. Okay, so the unit itself for velocity is meters per second. The unit also for velocity is kilometers per hour, or miles per hour, or miles per second, or whatever it is that's distance over time. Okay, meters per second will be the one we need to have for all of our equations going forward. So any other velocity unit that you're given, you have to convert it to meters per second. Okay, so that's why I gave you that shortcut to go from kilometers per hour to meters per second, because you'll need to have it in meters per second most of the time. Okay. Sometimes you'll see it just written velocity equals x over t. Oops. T, right? No change in. It's the same thing, right? If I just accidentally leave it off, I'm not leaving it off on purpose. It just means the displacement over the time. Okay? Because realistically, are we ever going to give a starting time and a final time? We're just going to give it took 20 seconds. Right? That's what the problem's going to tell you. It's not going to tell you the clock said 30 seconds when they started and 45 seconds when they ended. Right? That's not really how it's going to go. It's going to tell you that it took 10 seconds or whatever. Okay? So that'll just be what gets plugged in there. Okay. Do speed and velocity always have the same magnitude? No. Why not? Right, your distance or your displacement could be different. So we talked about the example where she walked 40 east and then 50 west. Right, her displacement is 10 meters west, but her distance was 90. So if she did that in 10 seconds, her velocity and her speed are very different things. Okay. Oh, man, I'm just ahead of the game. Okay. I don't think we need to go through the actual math that goes into that, do we? Probably not. We're going to do a practice one here. A person runs from a 50-meter mark to a 30.5 meter mark during a 3-second interval. What's the runner's average velocity? Oops. Okay, so here along the x-axis, here's 0, here's 50, 25. He starts here. He runs to 30.5, so maybe about here. So when we do our equation, we'd say velocity equals delta x over delta t. The final position, right? Delta always means final minus initial. Are we all good with that? Delta? Okay. So when we say velocity equals final displacement, what's his final position at? 30.5. His starting position was at a 50-meter mark, and it took him 3 seconds to do it. Okay, so if you don't have your calculator out, why don't you go ahead and grab that out so we can do this math. Got it? Okay. Perfect. Negative 6.5 meters per second. So in this case, what's the negative telling us?
Going backwards.
Yeah, he's going backwards or going west. Very good. So your answer could either be negative 6.5 meters per second or 6.5 meters per second west. I would take either one. Questions there? Simple enough? Okay. How far can a cyclist travel in a 2.5-hour trip along a straight road if her average speed is 18 kilometers per hour? Okay, so now let's start picking out what we have. Whenever I solve problems, I like to take what I have in the problem, 2.5 hours, so I'd say t equals 2.5 hours. And I make a list in the margins, right? Average speed is 18 kilometers per hour. That's still going to be kind of our velocity. We just don't have to include direction. Okay, so you don't have to write an S for speed. You can still write V for velocity. 18, I don't know why I wrote 1.8. 18 kilometers per hour. And we want to find how far. So what are we solving for? Yeah, x. Okay, delta x. And we can go ahead and keep it in kilometers. That's fine. You don't have to convert this one. Okay, so I question mark what I'm trying to find. So I would just set it up. 18 equals delta x over 2.5. Okay, when my variable's on the top of that triangle type equation, what do I do? Multiply that 2.5. Okay, and I know this seems simplistic and you could do these type of problems in your head, but we're building a foundation for when our equations get a little bit more complex. Okay. What did you get, 45? Okay. 45 kilometers. Okay, I want to do one other one real quick. Let's say I travel 32 meters per second for a total distance of 48 meters. How long did it take me to do that? Okay, what do I do when my variable's on the bottom here? Switch them places. So that means you say t equals 48 over 32. So it's backwards. Okay, switch those two places. Yeah?
Did you want the answer? Or
Sure.
It's 1.5.
1.5. Okay.
So on the one where it was negative 6.5 meters or whatever, you said it could be west.
Mm-hmm.
Could it also be south?
Well, since we knew he was running horizontally, we know it's west.
Okay.
If it was something that was dropped, then we would know it's south.
Makes sense.
Yep. Okay. And even though when we drop something, even though it might not be traveling south direction, we still think about it as going downward south. So I know it's kind of hard to like move your coordinate plane and make it, this way, so it's in front of you, but that's kind of how we do that.
Okay.
Okay. And we'll deal with vertical next class a little bit, but any questions? Yeah. I can, yes.